Let us start the analysis of continuation concept of standing wave ratio. The condition of standing wave ratio defines the relationship between the reflection coefficient and the standing wave ratio. How to go into the standing wave ratio? First, we will see the block diagram of a transmission line connected between the source and the load. When the wave is transmitting from the source to the load, it is called as an incident wave. After reaching the load, if it is getting reflected back, it is returned back. A ball bouncing from the wall is called as a reflected wave. So the diagram has two definitions, incident wave and the reflected wave. Now what is called standing wave? So standing waves are nothing but a combination of incident and the reflected wave. Again, the diagram very clearly depicts. Figure A defines the incident wave from the source to the load, and figure B defines the wave from the load to the source. So it is reflected wave, and a combination of incident wave and the reflected wave is what is called as a standing wave, is the figure C. Now we will see what are the points available in a standing wave. The standing wave has 2 points. One is node, another one is antinode. How to define a node? Excuse me. The node is a point along the standing wave where the wave has a minimum amplitude. So vice versa condition for antinode. If you have maximum amplitude, then it is called as an antinode. And the example is a real-time example is a guitar string. The ends of the string are called as the notes. So by changing the position of the end node through the frets, the guitarist can change the total effective length of the vibrating string, and hereby the note is being played. So in the second diagram, we have the representation of how many nodes and antinodes are available in the diagram. This standing wave has 4 antinodes because there are 4 maximas in the diagram. There are 5 minimas, and therefore it is called as a 5-node representation and 4 antinode representation in the diagram. Now we will see what is standing wave ratio exactly. Now if the line is mismatched, whenever I say line is mismatched, it is between source and load, but neither it is open nor it is shorted, then the voltage will give rise to analysis of mismatch. So there is a greater variation. So there are 2 standing wave ratios. One is voltage and the current. In general, we prefer the voltage standing wave ratio denoted as SWR, which is the ratio of maximum voltage to the minimum voltage, and the mathematical value is always greater than or equal to 1. Now we will see what is the exact relationship existing between SWR and reflection coefficient. SWR and reflection coefficient, we know already in the previous video we have seen the definition of reflection coefficient. Rho is equal to ZL minus Z0 divided by ZL plus Z0. In this video we are defining the SWR, which is the ratio of maximum voltage to minimum voltage. So the first mathematical equation, Vmax is equal to sum of Vi plus Vr. But Vi plus Vr can be defined by rho of Vi, because rho is equal to analysis of reflected and the incident voltage. So I am redefining the reflected voltage in terms of incident voltage. For Vmax, Vmin again substituted so that we get the general relation. SWR is equal to 1 plus rho divided by 1 minus rho, or rho is equal to SWR minus 1 divided by S plus 1. So the same mathematical equation is plotted in the graph. So first definition, we will see the relationship. SWR is always a positive real number, whereas the reflection coefficient rho may be positive, negative, or it can be complex. Always the value of SWR is greater than or equal to 1, whereas the magnitude of the reflection coefficient is less than or equal to 1. So there are 3 set of conditions. First, for a matched line, the load impedance is equal to Z0, so reflection coefficient rho becomes equal to 0. So the equation defines a matched line with straight line of blue representation in this diagram. Next, for a shorted line, short-circuited line or shorted line, ZL becomes equal to 0. So rho becomes equal to negative minus 1. So the value is a representation of short-circuited line. Same way, when we go for the analysis of open circuited line, reverse condition, the load impedance is infinite for open circuited condition, as a result of which the reflection coefficient becomes equal to 1, and therefore the wave is again shifted by lambda by 4 from the short circuited case. So this video clearly depicts the relationship between the analysis of SWR and the reflection coefficient. Thank you.